All matter is made up of atoms. The essential questions are: 1. What components make up an atom? 2. How are atoms of one element different from atoms of another element? The Greek philosopher Democritus was one of the first people to suggest the existence of atoms. He reasoned that atoms were indivisible and indestructible. Democritus's ideas were not supported by experiments. 2,000 years later, John Dalton conducted experiments to study the nature of atoms and came up with a theory to relate chemical changes at the atomic level. Dalton's ideas are the following. 1. All elements are composed of atoms. Atoms of the same element are identical. The atoms of any one element are different from those of any other element. 2. Atoms of different elements can physically mix together, or can chemically combine in simple whole number ratios to form compounds. 3. Chemical reactions occur when atoms are rearranged. Atoms of one element are never changed into atoms of another element as a result of a chemical reaction. We can define an atom as follows. An atom is the smallest particle of matter that retains the identity of an element in a chemical reaction. Today, atoms are known to be divisible. They can be broken down into subatomic particles. The first subatomic particles discovered by Thomson's experiment were electrons.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
If cathode rays are electrons released by atoms, and since atoms are electrically neutral, it makes sense that a positive charged subatomic particle must also exist. Positively charged subatomic particles are called protons.
In 1886, Eugene Goldstein performed an experiment using a discharge tube. He divided the tube into two chambers with a perforated metal plate. This plate acted as a cathode. An anode plate was placed at the other end of the first chamber. A small amount of residual gas was present between the anode and the cathode. When he applied voltage, cathode rays began to move from the cathode to the anode, and when they struck a gas molecule on their way, it emitted charged particles. These particles moved towards the cathode, passing through the holes in the cathode plate, and produced a beam at the back of the cathode. Since they moved from anode to cathode, they were called anode rays. Goldstein later tested these rays. He observed that in the presence of an electric field, the rays changed their path. They deflected away from the positive charge. This indicated that the particles were positively charged. Hence, he concluded the anode rays were composed of positively charged particles.
In 1932, James Chadwick found yet another subatomic particle, the neutron. Neutrons are neutral subatomic particles, with a mass almost the same as a proton's mass. The table below summarizes the properties of subatomic particles. An electron has 1 unit of negative charge and its mass is 1084 times smaller than the mass of a proton. A proton has 1 unit of positive charge. A neutron has no electrical charge and its mass is similar to the mass of a proton. Where are all these subatomic particles located in an atom? Rutherford did an experiment with a beam of positively charged alpha particles directed to a very thin sheet of gold foil.
A radioactive source was placed in a lead block with a narrow opening. The radioactive source is rich in alpha particles. These alpha particles are allowed to pass through the narrow opening. A lead sheet with a slit is placed just after the lead box. These fast-moving alpha particles passes through the slit and hit a thin gold foil. The alpha particles were detected using a zinc-coated fluorescent screen. When the alpha particles strike the fluorescent screen, they produce scintillations. This experiment, Rutherford observed that 1. Most of the alpha particles pass through the gold foil undeflected. 2. Some alpha particles were deflected at small angles. 3. Some alpha particles were deflected at large angles. 4. Very few of them bounced back at an angle of 180 degrees.
From this experiment, Rutherford concluded that 1. An atom is mostly empty space. 2. All the positive charge and mass are concentrated in a small region, which is called the nucleus. 3. The electrons are distributed around the nucleus and occupy almost all the volume of the atom. How are atoms of hydrogen different from atoms of oxygen? Look at the table showing atoms of the first 10 elements in the periodic table. Notice that hydrogen has 1 proton and oxygen has 8 protons. Elements are different because they contain a different number of protons. The atomic number tells us the number of protons in an atom. Most of the atom's mass is found in its nucleus. The mass of an atom depends on the number of protons and neutrons. The total number of protons and neutrons in an atom is called the mass number. Since atoms are electrically neutral, the number of electrons must be equal to the number of protons. Conclusion: the composition of any atom can be written in shorthand notation, using the atomic number and the mass number. In nature, 3 different kinds of neon can be found. They all have the same number of protons and electrons, but they have a different number of neutrons. The 3 atoms shown below are called isotopes. Isotopes are atoms of the same element, which have the same atomic number, same number of protons, but a different mass number, different number of neutrons. As we have seen before, the composition of any atom can be written using the atomic number and the mass number. Let's have a look at the gold atom. The atomic number is 79 and its mass number is 197. The atomic number and mass number allows us to calculate the number of protons, electrons and neutrons. In nature, most elements are found as a mixture of 2 or more isotopes. So, the atomic mass of an element will depend on the relative amounts of isotopes found in nature. The atomic mass is defined as the weighted average mass of the isotopes of an element in a naturally occurring sample. The unit of atomic mass is the AMU or atomic mass unit. It was decided that the atom carbon-12 has an atomic mass of exactly 12 atomic mass units. A carbon-12 atom has 6 protons and 6 neutrons in its nucleus, with its mass set equal to 12 atomic mass units. Let's calculate the atomic mass of the element carbon. There are 2 natural isotopes of carbon, carbon-12 and carbon-13. From the table we can see that carbon-12 has a natural abundance of 98.89%, and carbon-13 has a natural abundance of 1.11%. The atomic mass of carbon-12 is equal to 12 atomic mass units, and the atomic mass of carbon-13 is equal to 13.003 atomic mass units. With this information, the atomic mass of the element carbon can be calculated. Its value is equal to 12.011 atomic mass units.